All right. Thanks, Sagiv. Could give Sagiv an introduction, but what I would say is look for his piano playing videos on YouTube or Facebook or wherever he puts it. One of the most talented pianists I've had a chance to work with. Okay, so yeah, my name's Doug, and I'm going to talk to you about some challenges in building machine learning algorithms for the creative community. A lot of this is going to be overview of the machine learning in terms of slides, but I'm going to try to give you more of a view into how hard it is and also how rewarding it is to try to build out experiences for artists that they value and hopefully their viewers or their listeners value. And this talk is on the behalf of the entire Magenta team. Over the years, maybe 20, 25 people, including Sagiv, but really it's steady state, a pretty small group, six or seven people steady state. And if I drift a little bit, I'm pretty jet lagged. I flew in from Paris a couple nights ago. I didn't really sleep, so I have my intravenous coffee to keep things going, even though it's midday for me. If you have questions, I dramatically prefer if you ask as we go. I think it's especially with a Zoom call, it's nice to have questions interspersed so that we don't have the monologue effect. I can't see you, so I think Sagiv's going to monitor the chat if you want to chat, or you can just unmute your mic and say something. I don't care. I prefer that in live talks as well. So there's a bold claim you can make, and this bold claim is that machine learning is changing the way humans create music. And I think that the honest follow-on to that is maybe, sure, but maybe not, and time will tell. And in some sense, this talk is about, after 5 years, we're still not really sure, that is 5 years of Magenta, we're still not really sure whether this all matters or not. And by matters, I guess I would say whether we'll see a number of artists, whether musicians or visual artists or something else, use machine learning in a way that they believe enables them to do something they couldn't do otherwise, and that they liked what they could do. Bonus points for having followers. So maybe 20,000 other people like it as well. And the reason I think that's maybe or maybe not is that if you look at the history of tool building for the arts, for every successful tool, whether it be like a film camera or a drum machine, there are hundreds, maybe thousands of unsuccessful tools where people have tried to build that next art making device. And I think there's a lot to be said about what makes a tool successful. And TLDR, because I may not come back to this point, I think it's about a very interesting cyclic interaction between artists and technology builders. So a technology builder might build something like a drum machine, but it's up to the artists, maybe like hip hop artists in the 1980s, to turn that drum machine into something genuinely useful. And I think it's really unclear from the engineering side what you actually need to click with the arts community, partially because what the arts community is going to do is break what you built and use it in a way you didn't intend. And then you'll have probably this cyclic improvement of technology, but once the artistic community is dug in, then you're following them, even though you're the technologists who built it in the first place. And it's a separate talk, but there are lots of examples of this, including the motion picture camera, the film camera, even oil paints and tubes, enabling technology, initial resistance, rethinking how the art is made. So again, lots of researchers working on this. Please see our blog at g.co/Magenta blog for credit, but also just to have a look around. So what is Magenta? Magenta is an open source research project exploring the role of machine learning as a tool in the creative process. And so built into that mission statement is a bunch of what it is, but it's also quite a bit of what it isn't. So one of our non-goals is to actually make art and make music with machine learning. In other words, sort of push button, oh, I just pushed a button and I got another song that's as good as your favorite Radiohead song. Like, that's not our end goal. Our end goal is to enable new creative pursuits for people. And I think that's not just altruistic, though it is. It's like what we believe, but tied in with what I mentioned before, I don't think you can meaningfully talk about creativity without keeping people in the loop, having those people embedded in culture, communicating with each other. So, art, a song written today might be about the Electoral College in the United States electing Biden. And that's sort of maybe you're angry about it, maybe you're happy about it. And so you have something you want to say. And so that whole layer is missing, at least in the machine learning that we have now. Maybe we'll have a smart enough, embedded robot that will have that in a gajillion years, but we don't have that now. It's a project that I created, I guess coming on 6 years ago, as an antidote to getting burned out on doing music recommendations for Play Music. I thought, I don't want to recommend other people's music. I want to help make some new music. And it's been going in open source and in in academia and with connected to art projects for that time. And everything is at g.co Magenta. So this is what, just a screenshot of some of the things that we offer, work we've done. If you look at the date stamps on the blog, you can see we have a pretty steady cadence of output. Our blog is not insanely popular. We have about, somewhere between like 5,000 and 10,000 readers. We have a better following on Twitter, but we don't really care because we still have managed to position ourselves as one of the leaders in this space, and we've really enjoyed getting to know the community of creatives, a lot of JavaScript coders and musicians, and getting to know these folks. So tied in with our work, blog posts, demo section, a lot of Twitter interaction, and then our papers. And this is what our output might look like. And this is, I want to mention this because I want you to understand sort of where our priorities are. So this is Jesse, excuse my cough, at the beginning of last year, I'm sorry, at the beginning of this year, tweeting some work I'll talk about today, DDSP, differentiable digital signal processing. And what we have as part of that output is a blog posting, which is written for like a tech artsy geek community, some examples, a collab, all of the code and open source, and then a peer-reviewed paper. So these are our communities that we're working with in parallel. I think probably the most successful community has been the academic community. We've remained among a few labs that are doing, I think, pretty respected work in the space of music and machine learning, and a little bit of visual art as well. And we've found that that's easy, I think, partially because of the DNA of our group, which is Google Brain. So we have a lot of researchers to rely upon. We've had a harder time getting to the music community reliably, and that's a lot of what this talk is about. So what I'm going to talk about is a few things. First, I'm going to go over some of the generative modeling work that we've done for music and for drawing. And I'm going to highlight some of the aspects of this challenge that are relevant for the arts. So the first one would be learning an appropriate representation, mostly to enable user control, obviously to generalize, but also to enable user control. So think of providing knobs and levers for users to play with. Our strong experience is that artists get really frustrated if they don't have a way to control, in one way or another, the output of the model. And also caring about domain knowledge. We can talk about that in a true Bayesian sense, that we really know thy priors, but also in a more artistically motivated sense, that is, that we're trying to build tools for a community that we have some idea about their desires and their needs, giving rise to some common interaction patterns. So that's our talk. Again, if you have any questions, let me know. So first, for those of you who haven't been doing this work for as long as I have, there's been quite an interesting revolution in the quality of generated materials. So we can go back to 2014 with Ian's original GAN paper. And if you look back now, the quality of these faces at the top they're kind of funny looking, right? I mean, I think people forget just how quickly the field has moved. But it moved fast. I was extremely impressed by Alec Radford's 2015 paper, where they trained on images of bedrooms. And so now you have color generated images of bedrooms. And even on this image, if you're close enough to your screen, you can see reliable windows with lighting, you see beds, you see carpets, etc. And this blew my mind. I'm like, wow, I can't believe this is so good. But if we zoom in a little bit, this is what 2015 looked like. This is a 2015 bedroom, just upscaled to be a little bit easier to see. And now we're at 2018 with StyleGAN, and we've dramatically moved up in quality. So it's not just the idea of a lamp; you actually see lamps and geometry. And so this is 3 years. And I grant, with all of the face generation that we have coming up in a couple of slides, this may not seem that impressive. But if you're sitting back in 2014, I think it's hard to predict that we'll move as fast as we did with GANs. And of course, the StyleGAN work on faces is very interesting. It's also it's a little troubling in some ways, especially with the face generation. I think as as we move further along with this work, we see that there are some pretty large ethical questions, and just kind of like, is this really what we want to be doing? So that's another direction of discussion here, and it's definitely something that we're sensitive to on our team, and I think we're trying to keep up with the field and the implications that are made there. I want to mention some of the tech stuff too, given GPT-3, but let's realize that 2013 is not that long ago, and Alex Graves from DeepMind, I think he deserves credit more than anyone for getting the LSTM-based generative text off the ground. I was lucky enough to work with Alex as I was a postdoc with Jürgen Schmidhuber from 2000 to 2003, while Alex was doing his PhD, and can echo something he mentioned in a talk, that there were 3 of us in this room, myself and Alex and Felix Gers, and we were like the only 3 people in the world that still cared about LSTM. I moved away from LSTM when I became faculty at University of Montreal, and Alex, to his immense credit, just kept going. He just kept pouring energy into this until very impressively, this generating sequences paper yielded some kind of coherent text. So for some range of start rail years as dealing with 161, et cetera, I say kind of coherent. There's a little bit of topicality to this. That's 2013. Let's jump to 2019. And we see some of these famous GPT examples showing up, where given a human prompt of some unicorns in the mountains, we find that over multiple paragraphs there's topicality, and you'll even find that we're still talking about unicorns 5 or 6 paragraphs later. So this is very impressive in 5 years to have moved this far. Now, a lot of these recent advances in sequence generation, of course, come from Transformer, which came from our group, came from Google Brain. And in parallel with Transformer, we did Music Transformer, which is our attempt at understanding the implications of sequence generation for music. And one of the fun parts of this is realizing that because music has repetitive structure, so it has verses and phrases, stanzas, choruses, refrains that repeat, it's quite nice to look at what the attentional mechanisms are up to when they're learning musical sequences. And so one of our contributions to the field was to improve pretty dramatically the ability to transcribe recorded piano from audio into MIDI, preserving some of the timing and the dynamics, so you can hear the pianist. It doesn't sound completely robotic. And then, we have many millions of these. We have a data set that we released as well. And that gave us enough data to train a transformer. And so what you're looking at here, the arcs are the attentional heads of the transformer and what they're attending to, with the color of the line being which head, and the magnitude of the line being how strong the attentional connection is. And time's moving left to right. That's a piano roll. So you can think of the piano turned sideways. And you can see that at this point in time, the model's attending to a number of different pieces of information in the past to predict the next note. The other thing I'll mention is that besides the fact that we can turn it back into music, this really is a straightforward language modeling task. It's just that our language is a little bit weird. The vocabulary of our language includes words like press the middle C and move the clock forward a few milliseconds and make things a little louder or a little less loud. And with that, we can reproduce the piece. And I want to play this for you. And what I want you to pay attention to is less the quality of the music. This is a piece that sounds kind of, to my ears, quite high art classical. That's partially because of the training data. The training data was pulled from a particular tier of YouTube that we were allowed to work with. And that's all documented in the paper. But I want you to pay attention when some of these repeating segments come along, and you'll see them as little short dotted lines, that when we get to the second repeating segment, the model completely locks in on the first segment and uses it to its advantage to create a version that has slightly different musical characteristics.
Can I ask a small question before you start? Is this existing music, or was this generated by you? Because you mentioned that you don't want to generate things, right?
Right, that's correct. So that's a very good question. So this is generated. our goal for generating it is to understand how the model works. So we had, this is a bit of a tricky subject for us. But it's not meant. Okay, how do I explain this? This is a good question. Yeah, this is generated music, and we even put up a website that lets you randomly play from one of 10,000 generated pieces of music. We think the output is impressive, but I personally think, and the authors think, it's not musically interesting in the sense that we would ever want to like replace pianists with this. So what we're looking at is like right now, this transformer model is a decoder only model. So our way of controlling it is to condition it either with chords through special mechanisms or with someone else's melody. And then we can use this model to harmonize, to play along, to generate some segments that we can then play with on our own, or to provide inspiration. But yes, this is generated.
I see, thank you.
Sure. Oops, sorry. That doesn't work the way I thought it was going to work. I thought when I hit space, it was going to pause, but it went to the next. Well, in the interest of time, I'll move on. But I hope you can see that, especially this segment right here. Oh, you can't see my mouse. The segment just to the left of the YouTube play button heavily conditions the stuff at the end. I'm not used to using Zoom. I use Google Meet usually. It works slightly differently. Apologies. But in the interest of time, let's move on. It's already 20 after. So let me recap that. If I had a couple of other slides, what I could show you are two different ways in which Music Transformer can be used for some artistic purpose. One of them is that we can condition the decoder with chords. There are a number of ways to do that, where we can either insert chord tokens in the stream as we need to, or we can explicitly build in like a conditioning mechanism. We've also done infilling based upon a melody. So you have a melody like, you know, it could be Twinkle, Twinkle, Little Star. In some sense, as a demo, it doesn't matter. And then the model will learn to actually perform that melody in very, very different ways. I personally did something with Music Transformer that, as a musician, was really satisfying for me. It might seem a little weird, but I just sort of went through a bunch of examples of Music Transformer until I found one that I liked. And then I just used it as the basis to write a song. And what I liked about it was that it provided kind of interesting artistic constraints. I forced myself to keep the melody and the basic voicing of the chords that were present, and also to hold on to some of the ornamentation of the piece. But I took this piano piece and I turned it into, you know, like a pop song, basically a kind of slightly melancholy pop song written by someone who was stuck in an apartment for several months during COVID in Paris. I don't even care if it's a good song. For me, it was just a really interesting exercise, and I got a lot out of having this bass line that was this generated thing that I could play around with. All right, we're going to shift gears slightly. And by the way, I recognize the sophistication of this crowd. I purposely didn't make this a super technical math-heavy talk, because we would dive into these details that I think don't really get at the point that I want to make, which is, you know, a view of what it means to try to build tooling for artists, and what are the questions and what are the conundrums, and even I'm happy to talk about what are the ethical issues with respect to using machine learning in this space. I want to talk a little bit about latent spaces. I'll go ahead and define it. You know, it's a machine learned representation of a data distribution that maps to the high dimensional space from some lower dimensional space. And so, you know, the way I like to think about this is in the space of the data, there's a certain nonlinearity to how the data is distributed. And you can flatten that out and make it such that distance in the latent space maps onto some sort of meaningful distance in your world. And what we really want for our latent spaces is that the distances, the local geometry of the space is actually musically meaningful. So as you move around in that space, you're moving around in a way that aligns with your musical intuitions of how things should work. And oops. The first example I want to talk about, I think it's a really good illustration of how you can think artistically about latent space models, is David Ha's sketch RNN, or a neural representation of sketch drawings. And here's a pig that's drawn by his neural network and then colored with another colorization algorithm. So this pig does not exist either, just like those faces. And I think quite interestingly, the data that David worked with came from a game that Google Arts and or the Google Creative Lab put online a few years ago called Quick Draw, where you're playing Pictionary against the computer, and where they're storing with your mouse movements. So what you have is delta X, delta Y. Where's the mouse moving? And then did you just touch or lift or end? So touching is starting, lifting the pen, touching the pen back to the paper, and then you're done with your drawing. And so there's the data for that turtle that's been drawn. And so it's important to remember this is a sequence problem, and that importantly, I think the sequence structure actually captures a little bit about how people draw. And there was some really interesting analyses of the data done that's published in our Google blog, not done by the Magenta team, done by another team, but looking at, for example, how different cultures draw chairs differently, or how different cultures will happen to make letters differently. It's really fascinating to see the underlying structure to these simple drawings made in 20, 25 seconds by someone messing around with a Pictionary-like game. And if you have your sound turned on, all the while the computer's kind of yelling at you in a really annoying way. No, it's a pig. No, it's a trumpet. No, it's a turtle. And so, you know, the artistic depth of these images is certainly not deep, but they're still interesting to play with. And there are lots of them. So what we're going to learn here is some sort of encoder-decoder, autoencoder. We'll learn a latent representation. In this case, it's a VAE, so there's a variational loss added to the model that tries to force each dimension of the representation to look Gaussian. And this has the nice effect of forcing the representation to fill the space of the vector. And that means that you don't have too many dead spots in this space. So as you sample randomly from these vectors, you tend to get something reasonable. And so if we talk about just sampling from the decoder on the left, this is a model trained just on yoga. If we just randomly generate vectors and start to decode from them, then we get vectors at the top that are quite reliable. A lot of them look very similar in terms of the yoga pose. There's a lot of arms in the air. And then as we generate lower and lower probability vectors using a temperature control, we get crazier and crazier yoga. But in general, we don't get very many completely crazy images from this. And if you take away the variational loss, then you definitely do get lots of crazy images because your autoencoder is not forced to fill the space of the embedding space. Adding this noise term that forces each dimension to be Gaussian helps a lot. And then on the right, this also shows that the space is sort of changes smoothly with respect to some idea, I guess a perceptual idea of what faces look like. So we didn't do any human experiments, but this is just a demo of David's. In every corner of those images of those faces is a face that David drew. So upper left is this kind of potato looking head with a smile, and the lower left is a kind of triangular looking one, and etc. And then the rest of the faces are generated by moving linearly through that space on the hypersphere. And you can see that the faces, in my mind, move really nicely from one exemplar to the other. And then at the bottom, we have a similar move. Now we're going to move just from point A to point B, where point A is the profile of a cat, and point B is face on of a cat to the profile of a pig on a model trained on cats and pigs. And you can see that the model moves quite reliably through the faces, does a kind of interesting phase shift where one of the whiskers becomes the body of the animal, and then that continues to morph from cat to pig in a reliable way. So I think there's some interesting effects to be had here in these latent spaces if the data is right and the loss is right. It's kind of underlying artistic space of animals. And again, all of these could be animated, so you could force all of these to be drawn. They're all sequences of pen movements. They're not bitmaps. Also, these models, they're not, the latent space, of course, has to be some compression of the data. Otherwise, we'll just memorize. And if we look at relatively normal looking things like the cat body or the cat with the whiskers, things get reconstructed fairly normally. If you add 3 eyes to the cat, you're actually going to get back a cat with 2 eyes, because having those 3 eyes is pretty improbable. Now, if you draw a toothbrush, you're probably not going to get much of a cat. So that toothbrush doesn't embed very well. So, it yields a very low probability cat. I'll also call your attention to the second cat face. I'm sorry, the second image, the first cat face, and observe that on top, it has 5 whiskers, but it reconstructs as having 6 whiskers because the 5-whiskered cat is very rare. And then here we have some other human inputs that are, again, the pigs. The first 2 pigs are pretty straightforward. And then I really like the last one, the truck. So this is a class trained only on pigs. And if you take that truck and you embed it and reconstruct it, you get this truck pig that I think is really interesting. Like for me, if someone just as a joke, when we're playing Pictionary, gave you the class truck pig, I'd have a hard time doing a better job than that. I mean, I love how you still look like you have the cab of the truck, but it's sort of a pig snout. And now the wheels of the truck turn into pig's feet, etc. I think it's kind of humorous and a fun way to think about how these models work. I also think, the question you should ask yourselves is, do I want to play with SketchRNN because, it's an example paper. But imagine if we had much better drawings. Imagine if we had drawings by some artists. Maybe I'm a visual artist and these are like a bunch of my pencil drawings. Being able to play around in the space of my own art, that's something that's interesting for a number of artists that we've talked to, and we've talked to a lot of artists. And it seems like a intuitively interesting way, the idea of extension. We also have this idea that once we start a drawing, the red is the person drawing, David, that different classes like forest and face and owl and mosquito and fire truck, they'll all be completed in different ways. So you can take your idea and complete it in ways that can open up new ideas. I like this animation a lot. On the class of rain, it turns out if you draw a cloud, you'll almost always get rain coming from the cloud. And that's because a number of people, when they wanted to show rain in Pictionary, they first drew the cloud and then drew the raindrops. Almost no one draws the raindrops first and then generates the cloud. So it's kind of fun. You can make it rain. I'm going to move a little faster because time flies. It always does. This is another paper that came from Magenta called MusicVAE. This is Adam Roberts as the first author. And here the idea is to build a latent space that over musical measures, over bars of music, and such that similarity is preserved, musical similarity is preserved. This is also a hierarchical model and was intended also for language, though the language results didn't work as well as we liked. So Adam pulled those and we stuck only with the music results. And I'm going to play you this example going from point A to point B. So the way this video is going to work is you're going to hear a musical segment A in black and a musical segment B in black. And then the model is going to move from A to B in a straight line through the latent space in a way that's hopefully musically appealing to you. And for those musicians in the room, I guess even for those of you that aren't musicians, think about how you would do this yourself. It's actually, we've tried, it's quite hard. And from a musical standpoint, I think even though these are like kind of video game clips, actually, the ones that start and the end, it's quite cool how the model gets from point A to point B. And at the bottom, you're seeing the entire sequence unwrapped. And what you're going to see is the video playing itself out. hope you like that. I always find that to be a satisfying demo. Something works for me in that. A couple of things to observe is the note density. There were a lot more short notes in the last sample than in the first. And the model correctly adds more short notes per measure, gradually moves up, changes the contour of the melody from being roughly like an arc to being like a sawtooth. And all the while it makes some sense. So we've seen a lot of community demos in JavaScript done around MusicVAE, and it's a fun model. Okay, I'm going to shift gears now and talk about audio. In this case, this is more recent work from Jesse Engel and others called DDSP, Differentiable Digital Signal Processing. And here we're talking about let's do a slight recap because we're a little more than halfway through. We talked about this idea of having, very good generation. So I guess I would call it fluency with the music transformer. The idea that if we have enough data to fit, transformer-like models can give us the equivalent of like GPT-3-like fluency, but for music. We also have these idea of latent spaces, and can we find ways in which we can give users control by embedding into some space where you can move around and locality matters. Now we're going to talk about transformations and filtering. So can we take sounds and change the way they sound? So you might think of this as more of a style transfer-like effect. And the basic idea here is that we're going to find a way to do high quality synthesis without having to do autoregression, and it's super, super efficient. So with as little as 10 minutes of data, we can train a model that takes some target audio, runs it through a very bespoke autoencoder with lots of built-in assumptions about how music works, and then decode back the synthesized audio. And so basically what you'll see is that this image deserves a little bit of unpacking. The red, sorry, the red boxes give you the basic encoder-decoder process. The green boxes are showing you where users can add control. So F0 is pitch, Z is your embedding that gets passed through, and then loudness is how loud the sound is in time. And then the decoder, then when the decoder side actually has some musically motivated neural networks built in that capture what we know about, some of what we know about digital signal processing for audio. So for example, at the top, we have this harmonic audio decoder that is explicitly built around this idea of combining weighted sinusoids to generate a sound. And that gives us our harmonic components. We also specifically capture the aharmonic parts of the sound. For example, the scratching of strings on a violin bow. And then we also pass them through a reverb unit. It's a neural network, and we propagate a gradient through it, but that neural network is built based upon what we know about how real digital signal processing reverb units are built with delay connections. And then this whole loss is passed through the network backwards, pulling out as much of the signal as we can with our harmonic audio, filtered noise, and reverb components, and also giving us a latent space to play around with. And this model has been quite impressive to play with. So let's listen to a little bit of this. This is a piece of real audio, a piece of recorded violin. And here's the quality of the resynthesis. To show you that the reverb unit is doing something, we can zero out the reverb, and we should get something with no echo. And then here's the additive synth part. So all of the scratching sounds, all of the non-harmonic components are going to be missing here. And then here are the noise components that were captured by that filter. So the way to think about it is our resynthesis is formed of the additive component plus the noise component and the reverb component. But crucially, we get two things from having these broken out in separate boxes. First, users can control these. So they can decide that they want to turn off the reverb, or they can add different kinds of noise. And it's also quite efficient. So these models are very small compared to like just doing this with a big wavenet or something like that. And then these are the two signals that we can control, the F0, the frequency, and then the amplitude. So So that's the basic idea. One thing I like about this, so I'm not on this paper, so I can brag about it. I wasn't able to contribute to writing the paper, so I didn't feel comfortable being on the paper. People have been trying to do this for a long time, and I've talked to a number of labs who are like, this is great, and we've been trying to do this too, and damn it, you got there first. I mean, it's pretty obvious idea to be inspired by good old-fashioned digital signal processing. If you look at signal processing circuits, they look like neural networks. But getting the details right and understanding how to build the right filter chain and calculate a gradient through it was the big contribution that Jesse made and others. This also was something that generated like some fun demos. We did something called tone transfer, which I'll have a slide for later, which was a website, an experience built for all users, not just machine learning folks, and that allowed them to take a sound like trumpet and turn it into violin, etc. And then this is a YouTuber that did a little video about it. So I'll play this for you.
This video was brought to you by Skillshare. Okay, so I saw this Andrew Huang video recently where he turns the sound of his voice into the sound of violin using AI. Okay, dang. Andrew's using a tool that was developed by Magenta, which is Google's AI and music research division. They were the ones that were responsible for that Bach AI chorale doodle thing. They have tons of really interesting projects, but the one that Andrew is using is something called tone transfer, which can transform the timbre or the tone of one audio recording or instrument into the timbre of another one, a completely synthesized one. The best way that I can understand it is that they're using machine learning that has been trained on the sounds of violins or saxophones or different timbres, and then combining that machine learning with traditional understanding of synthesizer technology, additive synthesis, subtractive synthesis, filters, oscillators, etc. So basically the way that this works is you can go to their web widget thing that they developed and just record yourself talking or singing or doing anything like that. I'm just talking right now. And then you click done. I'm just talking right now. Let's transform that into, or doing anything like that. I'm just talking right now. And then you click done. Improvisational jazz trumpet, baby. I'm sure you can make some spicy memes this way. I wonder what steamed ham sounds like through the AI.
Well, Seymour, I made it, despite your directions. So.
That's enough. So you get the idea. That gives users some control. Okay, I'm back. I'm going to shift gears again and talk about some of the patterns that we've seen on the user side. So how have people been using things like DDSP, MusicVAE, etc. And with the idea that, I don't think we've gotten this right yet. A lot of our research has pivoted towards HCI and UX, trying to understand how to put this work into users' hands. But I want to talk about a couple, I guess 4. This idea of extension, extending something that you already have, curation, choosing among things that the neural network has given you or the model, imposing constraints artificially to make the model do something you like, or transformations and filters like we just saw. So let's keep diving in on this. Okay, so extension. This is a screenshot. It's actually a video I'm going to play for you from a suite of tools that we built called Magenta Studio. And Magenta Studio is built up of 5 different units that can work in MIDI to do something like, for example, generate drum loops. And our goal is, we're only halfway there. Our goal is to have tools that fit inside of Ableton, which you're seeing here, one of the more popular digital audio workstations, and that give users tools that they can use as part of their music making process. And so I really like Drumify. What Drumify will do is take any sequence of events and try to build a reasonable drum pattern around those events. It'll treat it as something someone drummed and try to turn around and make a more complete drum piece out of it. And the idea, what we did was we recorded drummers, we paid them, they came in the studio, they gave us about 10 hours of drum music, and we trained up a model. And now this is able to take something that I've made and grab some of the rhythm and extend it for me. And so for me personally, Drumify is really cool because I'm not very good at drums. So I can lay down a bass line, or I can do stuff on keyboard or even guitar. But to be able to take that and have this unit generate some interesting and pleasing drums for me is really cool. So I'm going to play this for you. And what you're going to hear is some music being created. And then it's a live demo. We're going to call out to Drumify, and Drumify is going to create some drums. And given the drums that it creates, it's worth asking yourself, you know, how would you do the drumming? And does this do something better or worse or different or interesting? And just kind of see what you think the model does. So. So that's John, who played the bass. He's the intern working on this. Now Drumify is making some drums for that bass line, kind of funky bass line, by finding the onsets and using them as if they were drumming onsets. So for me, as a musician, this is a genuine extension. I've played with Drumify a lot. I've played with it with guitar. By the way, so you have a better idea of how it works. That drum, that bass line is acoustic, and Ableton itself has a feature that'll detect the onsets of the notes, so that is basically turned into. And then from there, the Drumify model is taking the MIDI, which is just the onsets. There's no instrument assigned to those onsets. They're just events in time. And it's trained to try to infer what would be the drum sequence that generated those events in time. So it'll decide where to put a kick drum. It'll decide where to put a hi-hat. It's able to generate from the basic kit of snare, hi-hat, kick, and tom, I guess. And so, you know, it's doing its best. And you also have a temperature control, so you can make it a little crazier or less crazy. And so I just had endless fun playing with this. For me, it's genuinely extending. Whereas if you're a drummer, you might not care, right? Because you can do it already. And I like that idea of, you know, one thing we found is that the arts world is incredibly high variance. So there are lots and lots of different ways to make music and to make art. And in some ways, you have to decide who your crowd is and who you want to please, and not try to please everybody. Another really cool pattern that I like is the curation approach, which of course is nothing new. But the basic idea is you let the AI or the machine learning make something, and you decide to reject or accept. You know, you do rejection sampling, but if you actually accept, then you use it exactly as is. You don't modify it, and that provides a nice constraint. What I'm gonna, the best example I have of this is an album, an entire album called Chain Tripping, done by the band Yacht. They're a pop group from Los Angeles. They're in no way famous, but I really love their music, and we worked with them for quite a long time on this. And they used lyrics generated by Ross Goodwin, not from Google. All of the cover art is generated by Tom White, an artist in Australia. And then all of the drum sequences and chord changes and melodies were generated by us. So they played everything, and they heavily curated it, and they completely own it. Like they know they made this, not the AI. But for Claire Evans, who's the lead singer, and also, by the way, the author of a really cool book about women in the internet called Broadband, required reading. You know, her main thing was curation. So she printed out like tens of thousands of lines of lyrics generated by an LSTM model. And then she just chose ones she liked. And Jana and Rob, the two people doing the non vocals, did something really similar. If a drum beat was generated, they use it exactly as is. And even one of the comments that Rob made, who played, well, they both play bass, but was that sometimes the model would generate sequences that were really hard to play. So that's because the model was trained on all sorts of music, not just, for example, music for the bass guitar. And so they've generated these bass lines that aren't very easy for the hand to make sense of. And so that was one thing that Rob said, was like, yeah, like these things are hard to play on stage because they don't contain the constraints of like where your hand should be on the fretboard. I like that. I think it's something to fix because, you know, we could encourage constraints like that to make things easier to play. It's also just kind of interesting. So I'll play a little bit of this just to give you an idea of what the music sounds like. Oh, the last thing I want to mention before I hit play. Also, I loved their progression with how they treated machine learning and artificial intelligence. We, when we started working with them, their story was that they were going to do this AI album, and then they weren't going to tell anybody, and then they were going to release the album, and there was going to be this big reveal, and they'd be like, yeah, but it was really made by AI. And then as they started working with these tools, they realized, you know, it's a lot of work, and this AI is not quite as, you know, magical as we thought. And, you know, they felt like it was theirs, and they had no reason to like do this big reveal. So they just talked about the process. And I was talking with Claire at at kind of a festival, and I asked her if, you know, would she have more fun doing this now that the tools are so much better. I told her about how much more fluent things had gotten. And she's like, oh no, what was fun was just like how weird and you know, glitchy these things were. If it could write lyrics as well as me, I wouldn't want to use it. And I love that. You know, I think that's true. I think it's, you know, in so many, you know, musical settings or artistic settings, you really want the glitchiness and you want the edginess to be there. So let's play a little bit of this for you just to encourage you, hopefully, to listen to the album later. It's a very good album. Oops, or not. Let's see.
Drops so heavy in a tiny sea, I feel like I'm living in pieces, like a million people. I was born to lose control. Instead of I got caught up in a club. We got caught up in time flies away. I can't hear all of your eyes. Dreaming on me. Time flies away. I can't hear all of your eyes.
Okay, that's enough. I really like the album. I also like the idea, this comes from the same artist, Tom White, that did the cover for the album, really phenomenal artist in Australia. And he really loves this idea of adding artificial constraints to the process. I mean, really, in this case, it's a form of like artistically motivated compression. And what he does is limit the number of brush strokes his agent can make. The agent is trained on some sort of L2 loss over an image, and it's trying to learn what strokes to make. And it's all about artistic effect. I mean, there's lots of folks have worked in this space. DeepMind has done work in this space. You know, the idea of like a compressive model that limits the number of strokes it can make is not new. But these are the kinds of images he generates. And just take a second and go through and see how many of them you can guess. Like, what are they? The upper left is a heart, and then it's cabbage, and then it's I have no idea. I love the bottom fourth one over, that's a hairdryer, etc. And they're all limited to a certain number of strokes, and then for artistic effect, he limits the layering. So the model's able to lay down some larger brushstroke backgrounds, and then is able to lay down some black line accentuations. And it's all about constraint here. I think it's just a lovely use of fairly simple machine learning. Not to, I mean, it's really wonderful. I'm a big fan, but it's about how it's executed. Okay, and then finally, filtering and transforming. We already saw the tone transfer demo, so in the interest of time, I didn't include it twice. But the basic idea of like, can you take your voice and transform it into some instrument? And if you go back and look at tone transfer, you can Google for it, you know, play around with it. It's really fun. There's also a collab. One thing that people haven't picked up on yet externally, probably because they're not machine learning folks that are playing with this, is that you can train your own models. All you really need is 10 to 20 minutes of audio that you care about. Ideally, a single instrument or a single voice. The model will extract F0, the pitch, and it'll extract the amplitude envelope, and then it'll train up a DDSP model that you can then use in JavaScript to play around with. So that's nice. So where to next? You know, there's just so much more to say. I was selectively chose things that I wanted to talk about today. I think we need to think more like musicians and artists. A lot of the work we're doing now is trying to understand what are these workflows, how can we understand how to build for them, and how can we provide artists and musicians with a path from point A to point B, where point A is starting and really loving playing around, and point B is actually learning one more new skill on some pathway towards mastery. I also think we need to think about the form factor and the user interface. That's why I put up a picture of these guitar pedals. If you're not familiar with guitar pedals, any rock band guitarist will have a number of pedals on stage on the floor that allow her to turn on and off some effect or to change the loudness of the guitar. And it's like the perfect user interface because, you know, your hands are already busy with the guitar. So you need something that you can use your feet for, and it needs to be sturdy and bulletproof. So usually what'll happen is they'll take a number of guitar pedals, connect them with small patch cords like you see there, those little cords, and then often even just screw them down to like a piece of plywood with some carpet on it. And so you have this like board that's physical that has this signal processing chain built into it that you can turn on and off with your feet. And you know, it's immensely easier to play with. You know, all of these could be replaced with a laptop, but no guitarists that I know of have replaced their pedal boards with laptops. So that's a lesson for us. How can we make things physical? How can we build form factors that make sense for our listeners and rather for our users, and also just make it fun? Good, I meant to push this up. That should have been higher up. So these are the 4 Magenta Studio plugins that are in Ableton now. And we continue to refine this and try to make these digital versions easier to use. And like, actually in the next year, I'd love to build a guitar pedal that, you know, there are a number of open source guitar pedals that you can already buy that allow you, maybe it's a Raspberry Pi, to load some code. And then we can take over the buttons and pedal switches and play around with like a DDSP based on-stage guitar work. You want to learn more? Please visit our site, g.co/magenta. I'm on Twitter at @DouglasEck_, and my work email is deck@google.com. These are some of the folks that work on Magenta over the projects that I talked about. Might have missed one, apologies for that, but this is some of the team. We're definitely not a division. I don't know if, and probably you didn't notice, but the YouTuber was like, we're the music and machine learning division of Google. I'm like, I don't know, I don't think like 10 people makes a division, but we are what we are. So thanks for your attention, and I think we have time for questions now.
Thanks so much. That was awesome. And we do have time for questions. And there was one question in the chat earlier just asking about the MusicVAE sample and whether that was on Spotify.
No, but it's on YouTube. I can ping you I think if you search for MusicVAE Magenta, you'll find it on YouTube. If not, like through you know, like Sagib, I can always find it for you and send you the URL. I just don't want to.
Yeah, I replied with a Magenta link to it. So.
Okay. Oh, you found, okay, that's cool.
Yeah. So I will ask a question. At the beginning of the talk, you said like even after 5 years, and I forget exactly what you said after, but it was sort of like saying that even after 5 years, still there was like, you know, certain challenges. And I just wanted to put that in context of probably no musical instrument has been built in anywhere near that short of a time.
Yeah.
So, and usually it's sort of a generations of evolution as like somebody learns to play with it and then they realize it doesn't work that well, then it goes back to the instrument builders. If you have any thoughts about like what could even be done in such short time periods? I mean, obviously a lot, but any other thoughts?
Yeah, it's a good It's a good question. So first, I think you're right. 5 years is not a long time because you need these cycles of usage. The one word that comes to mind that probably could have come up in the talk earlier is like the idea of like building a grammar around a tool. So I don't mean like a linguistic grammar, but if anybody on this Zoom has ever taken a film class, they'll talk about like the grammar of filmmaking. You know, like using a montage, a set of short clips edited together to indicate the passage of time, or like well accepted ways of placing cameras, so that, you know, if you have 2 cameras, you place them this way, it's a 2-camera setup. If you have 3 cameras, you place them this way, it's a 3-camera setup. And people have kind of figured out the optimal ways to set up the cameras so one camera can't see the other and you can kind of cut between them. And we don't have those grammars yet, right? We don't really know how to use these tools, and we're seeing slowly, you know, these like usage patterns evolving over repeated use, and that's kind of interesting. And you're right, it just takes time. The drum machine was the same, like well, anyway, I'll stop, that's enough.
I'll read a question that I see from Mika. Fantastic work. Can you elaborate on some of the technical difficulties you encountered in learning representation for music?
Yeah, so 2 good stories. One of them is with Music Transformer, just realizing like how important it is to have enough data that you don't overfit. Sagiv, you were around for this. You know, Anna Huang, the main author of Music Transformer, she just couldn't get these models to do anything interesting. They would overfit right away, or they would underfit and be boring. And she was talking to Noam Shazir, who's one of the key architects of Transformer, and he was just like, "How much data do you have? You know, how many tokens?" And I don't know. She was playing with Bach, and he's just like, "Stop! You don't have enough data. Don't even bother." Right? So like, you know, that was one of the reasons that you know, we started caring about doing you know, actually generating more data. I think one of the other big challenges we have is in learning representations is a couple of times we've tried to work with people that, you know, gasp, don't want to do like Western art music or Western jazz or Western pop. They care about like Indian music, or they care about Chinese opera, or this, in one case it was like Afro pop, and then like traditional African musics of different sorts in sub-Saharan Africa. And in every single case, this goes back to data, but it also like it's on us to do better. Our models, like there's so much prior knowledge about Western music built into these models that's really, really hard to move away from it, down to the point of like the musical scale on the piano that you play so often, Sagi, is like kind of baked in. Like you could get around it, but it's there, at least for the MIDI stuff. And then the third one is music's no different than text in terms of like, I think as humans, we see the hierarchical structure very effortlessly. Like very few of us are confused by a simple song that has verse chorus structure. We're not surprised that the verses repeat, you know, and then the chorus, you know, the verses and the choruses interleave. And it's so easy for us. You know, we're really good at it. And it's just really, really hard to get hierarchy right. And that's a deep machine learning problem going back to hidden Markov models and before. It's been something that speech and language has wrestled with, and it's also true about music. It's just really hard to learn hierarchy, for machines to learn hierarchy, and really easy for people to learn hierarchy, it seems.
Yeah. Even things like the bar structure that MusicVAE assumes is an extremely strong prior that doesn't apply to a whole lot of situations, but it works great for MusicVAE. And
yeah, that's right.
Yeah. Another question, comment. Super awesome. As a guitarist and sampler, the drum generation is a huge development. Thanks for the great talk.
No, thank you.
When you publish, how do you evaluate? User studies? What forms of non-user-based quantitative evaluation?
That becomes a problem for us. We've been lucky, I guess, that our models have sucked so much, so to speak, that we've been able to rely upon like reconstruction error plus a few user studies to know if we're moving in the right direction. But we will soon get to the point where we really don't have good evaluation metrics. and it's on us to figure out how to handle that. One answer is that you have, if you can get enough people to use your tool, then you can start looking at user satisfaction as a metric in and of itself. And it may not be differentiable, but you may have some signal, if you can A/B test, to where you can slowly hill climb on quality by really listening to what sequences users tend to employ as musicians, or what edits they make. Like, there's all sorts of feedback signals you can imagine, but that's far off. I will say this is a common problem. I know for the text-to-speech work that's happening at Google and elsewhere in the community, the TTS quality post WaveNet has gotten so good that you're having a hard time. Like, you have two models, and you have a hard time, even if you go to like trained listeners, distinguishing whether model A is better than model B. That's a problem we don't have yet in music. I think our models are just, they still underfit pretty dramatically, kind of like GPT-3. Like, most people can tell machine generated text reading it for a paragraph or so, and the same thing's true for music. But if we keep moving, and if the vector is going in the direction I think it's going in, that's going to become the major limiter is evaluation.
Yeah.
Oh, let me say one more thing about that, kind of a cool story. So if anybody saw the Bach doodle from Google where you can harmonize Bach music, the paper from that was called CocoNet by Anna Huang, who's in Montreal. And when we went out to listeners, we asked if like how Bach-like they thought the music was, and the bass line was real Bach. And maybe not surprisingly, if you kind of unwrap it a little bit, many times the generated CocoNet Bach was treated as more Bach than Bach himself. And so, like, never once did we think, victory, we're better than Bach. It's more like you dig in a little bit and you realize that these aren't Bach experts, and that, the models are picking up on tropes, they're picking up on stereotypes. And so, yeah, like, probably any reasonable grad student composer could make something that to someone who just doesn't care about Bach sounds Bach-y, because it's got all of the tropes built in. And so stereotypes and subtlety and what your listeners want and how sophisticated they are matters a lot too.
I think context probably matters as well. So sometimes evaluations on a 5-second clip, even a 10-second clip, is not, in some cases, it's not nearly enough to actually evaluate for a person to kind of assess what's going on, or how does this compare to something else. It's sort of like if you jump into the middle 10 seconds of an action movie at the climactic sequence, it's not going to make a whole lot of sense.
Right. Yeah, that's so true. That's so true. Well, that's also like that's one reason I'm not worried about machine learning taking over the art world or the music world, because fundamentally it's based upon our own ability to mix surprise and predictability, right? And so if it's completely unpredictable, like if you took a time machine and took Andy Warhol's paintings to like 13th century France, the predictability would be so low. It's hard for me to imagine that people would get them at all, right? It would just be too far away. So yeah, there's a lot about getting that entropy mix right.
Another question from David.
Oh, actually, Sagib, I turned on the chat. I can see it now. I couldn't see it when I was presenting. Cool. Thanks, Misha, for saying thanks. So you want me to look at David Rockaby, right?
Yep.
Yeah, given that you find yourself moving more and more into HCI, do you see potential applications for machine learning in tuning the HCI itself? Absolutely, like thoroughly. So I think the whole idea is to build out an understanding of what an artist wants to do with the technology, and then build the technology, especially the user interface, in such a way that it allows for the machine learning to understand, allows for us to get the right signals back from the user so that we can improve the process. So I have this idea of like, a lot of people are calling it user in the loop, HCI. We chose to call it AI in the loop because we wanted the user to be in control and the AI being the thing that we're looping. And I'd love to be thinking about ways in which we could, use the machine learning. So like, it's, by the way, one term is systems HCI. That's not exactly this, but the idea that the HCI researchers are really fluent in the technology being used. And then you're trying to understand how to like close this feedback loop. And for the arts especially, I think especially if we think about things like creative writing, it's so crucial to close that feedback loop in a way that users have total control over, is transparent and is privacy preserving, right? Because you're talking about like people's creative writing or the music they're making. But if you can do that, I mean, one option is that the data never gets uploaded to Google. It's just part of the guitar pedal, or it's part of your user interface. Then the idea is like, you can't succeed unless you're doing both at once. Like it's silly to like ignore the machine learning and only care about UX, and you can't ignore the UX either, or the HCI part. It's all one system. And it looks like, are there particular challenges in lyric generation distinct from either text or melody generation? That's a good question. So I think there are two layers to this. One layer is that, sure, I mean, lyrics are poetry. So for lots of lyrics, you're caring about rhythm and meter and rhyme, like that layer of how the words fit together to accent the music. And that's a hard problem. I think more importantly for me, at least, is that, you know, a lot of lyrics in the rock and roll world are about sex, drugs, and rock and roll, right? Or you have hip hop. And personally, I'm uncomfortable. I'm uncomfortable with two things. Like, I don't want to sanitize lyrics. So I don't want to build models that are like autocomplete that says, you know, ducking. I never want to say ducking, as you know, the internet meme is. When you know, I don't want to like de-vulgarize music, but I also don't want to be the person that adds that. So like there's a stochastic nature here. I don't want to generate something that is racist or sexist or misogynistic or whatever. And I don't think that you can have one without the other. I mean, you know, like it's not that I feel like the world needs to have room for more misogynistic music. I feel just the opposite. But I don't understand how to create that lyrics generator that gives you the expressive freedom without opening up that door. You know, so I think that's really challenging. I also feel like maybe that's not the role of academia or of companies like Google. Like, you know, eventually these models will be out there, and if people on their own want to train their own models to do what they want to do, that's expression, and people can do what they want. You know? What are your thoughts on potential copyright concerns with generative models? It could be the case, for instance, it could be the case that the model has overfit to the training data and is regurgitating existing works. Is there a way to control for this? Oh man, that is like the big question. So the answer is no, not perfectly, of course. So if I trained only on whatever, the Beatles, and I generate something, right, it's pretty hard for me to think that if all I trained on were like, you know, 300 songs, I wouldn't overfit. You know, I think that's true already with sampling. So my take on this, my real take on this is let's not make things worse. I was part of like a copyright panel in Europe before everything shut down. And people were like, yeah, but what's this going to do to music? And my main answer was, first, let's not make it worse, and let's make it a little bit better. The point being that the existing system around copyright for musicians is a train wreck. Like the way musicians get paid for their compositions, the way musicians get paid for their performances, the recording rights, the way that this contracting works with the labels, this whole thing is a train wreck already. It's like balkanized across the world in different ways. And like, so it's already a mess. As we move forward with AI and machine learning in this space, let's first not make it any worse, right? And then second, can we improve? Well, we do have some tooling available that we can continue to improve, like fingerprinting exact matches or fingerprinting soft matches. Like, can we find covers, right? And then can we hold ourselves accountable when the machine learning generates something to at least be no worse than like a bunch of cover bands stealing your music already, right? And then you can imagine building layers and layers of control. Though fundamentally, the answer is, you know, like, no, we can't stop copying. Yet, yes, copying does seem to be a pretty important part of art and music, because if you don't capture some of the existing information in the system, right, then you're not going to be able to generate something that is understandable by your users, right? So your ability to like have this mixture of surprise and predictability, you know, like, you know, you would only generate music that just made no sense to anyone. So like you have this, there's a whole bunch of questions in my head, but the hard answer is no, I don't think we have ways to, to control. I think we can do as, you know, we can be responsible as well, as much as we can, but there's no proof behind it all, unfortunately.